I mean, it might not appear complex, but this does represent a Newton's first law problem, that our system is at rest. If you reduce the mass to a dot and you begin to draw your forces, it sounds like you had two. So how many of you drew a downwards arrow? Good, most of you. That's a start. What did you label this one? Weight. Excellent, W. And did anybody draw an upwards arrow? Excellent. When you drew the upwards arrow, did you attempt to make it the same size as the downwards arrow? Yes. Good idea. Good idea, trying to be consistent. And what did you label this one? T. Excellent. So as a Newton's law system goes, tension minus weight equals 0. Does that make sense? Okay. Now, if I had put a smaller weight on the spring, do you think it would have stretched as much? No. So there appears to be some relationship between the tension and how much a spring stretches. And this has a name. It's called Hooke's law. Not all springs obey Hooke's law, but a Hooke's law spring would. I know it sounds silly. What do you mean, Ms. Shelton? I'm saying anything that has this same pattern would follow Hooke's law. And that pattern is pretty simple. It's linear. But here we go. We'll take our simple idea that if you double the weight, we double how much the spring stretches and make it overly complex. First, we put F with a little s here to say force of a spring. Put a bar on top of it to remind us that it's a vector quantity and it has direction. Anything that's a direct proportion has a proportionality constant. And so our proportionality constant we choose to use here is a lowercase k. And I mean, we really stretched for the name. It's called a spring constant. And then to make it what is it proportional to? It's proportional to how much the spring stretches, delta x. So we doubled the weight, it doubled delta x. Unfortunately, delta x is a vector. And the force from the spring is in the opposite direction of what direction the spring stretches. So all of these things have to be taken into account when we deal with the spring. The spring provides a force that's in the opposite direction of the direction it's stretched or compressed. Springs work in both directions. You push in on a spring, it pushes back out. You pull out on a spring, it pulls back in. That's why there's a negative sign there. If you displace a spring downwards, it pulls upwards. If you displace a spring upwards, it pulls downwards. That's all that's saying. And I'm watching the room not write any of those things down. Look, those are the silly details that you should know. It's the extra stuff that fills in what this equation is to what's the truth about this. So I'm going to say those things again. The negative sign there is to indicate direction. The force from the spring is in the opposite direction of the displacement. If you push in on the spring, it pushes out. If you pull out on the spring, it pulls in. That's all it is. But that's how you write that. It's a direct proportion, and it has the force and the displacement. Now, there's things here that I want you to know too, like the spring constant, that proportionality constant. That's how hard the spring pushes. A higher spring constant would be a spring that pushes more. It would take more force to push it in or pull it out. So if K gets bigger, it's more difficult to deform the spring. Also, if you're careful, if you look carefully, you'll notice that K is the ratio of force over displacement. It's a ratio. If I solve that for K, get rid of the negative sign and all that garbage, just solve it for K, I get force divided by displacement, which has units of newtons per meter. It's the only thing that we will see that has units of newtons per meter. So if you're given a number in a physics problem and the units are newtons per meter, that's the spring constant. I'll say it again. If you're given any number in physics, the only thing that has this. If you're given any number in physics that's a newtons per meter, it's a spring constant. It's going to be a spring. So going back over here, I added a 0.2 kilogram weight to the end of the spring. Can you tell me how much tension the spring must have provided? Take a moment, try. The mass that I put at the end of that spring was 0.2 kilograms. How much force did the spring have to provide? I'll call on one of you to up the little level of concern of all the people staring at the front of the room thinking I'm not looking at the back of your heads. So the net force has to be 0. That's where we came up with this. If I solve this for the tension, which is the spring, I would get the tension equals the weight.
Yeah.
How do I calculate weight?
Weight, it's like mass times gravity, right?
There we go. Now we're working. This will be equal mg. All right, so we're getting somewhere now. And in this particular problem, the mass was 0.2. And what are we using for g here?
Would be 10, right?
Yes, it would be 10, right. So that'll be 2 newtons. All right, excellent. So the spring provides 2 newtons of force. Newton's laws are only good for letting us know an individual force or an acceleration. In this simple problem, we find that the tension from the spring is 2 newtons. But the spring obeys Hooke's law, which means that that tension is based on Hooke's law, which is minus K times delta X. Now, when I go over there and look at it, the spring is stretched 9.5 centimeters. You should be able to tell me what the spring constant is from that information. The spring is stretched out 9.5 centimeters. Be careful. I gave it to you in centimeters. You're probably going to have to do some work on that too. And if you don't know what I'm giving you, I'm telling you the spring has gotten bigger by 9.5 centimeters. It's got to be one of these numbers here. I'm not telling you which one it is, but I might be showing you. Now, I'm trying to show you that there's more to these. Getting just the picture right, it's just the start. I mean, I'm going to write this as minus K. Delta X is how far the spring was compressed and in what direction. What direction did the spring stretch out? Up or down? So I need to make that negative because it was stretched downwards and we made downwards negative. And it's 9.5 centimeters, but we have to put that in meters because newtons are in meters. So 0.095. And that equals 2. So you should be able to figure out what K is. Go ahead.
I don't know if, I don't think this is right. I got negative 21.05.
Well, 21.05 is right. The negatives will cancel out here. So the value for K will generally be a positive number. And you're right, 21 newtons per meter will be the units. Yeah, that's it. That's all I wanted. I want to remind you that Newton's laws tell us about force, but once we have information about force, you could be asked to do other things. Now, there's a lot for me to add to this. Things like if I was to try and take that stand and accelerate it upwards, would the string get longer, shorter, or stay the same? And I know some of you are trying to put the calculator on top of the book. And then opened up or turned the cover of the book. So that it looks something like that. I'm asking for you to draw the forces as they act on the calculator. And before you launch into it, is this going to be a first law situation or a second law situation? First law situation, sure. The calculator carefully just stays there on the book. So this is a classic inclined plane problem. Oh, how physics loves their inclined plane problems. Now you should be done drawing your picture now. If I reduce the calculator to a dot, how many arrows am I going to draw? Well, nobody? 3 sounds reasonable. Tell me one of them.
Weight.
So how do I draw that?
Downwards.
A downward arrow representing the weight. Excellent. Can somebody else tell me a different one?
Friction.
Friction. All right. How would I draw friction?
What the equal is. Same size as that weight.
I don't think so.
Friction would be down as well, right?
Getting interesting, getting harder, I guess. Let's start at the top. Is there any strings or ropes connected to the calculator? So do I draw any arrow for tension? No. Is the calculator in contact with any surface?
Yeah.
Yes. So I must draw a arrow indicating normal force. I don't get any choice about the way I draw this. Normal force must be perpendicular to the surface. So that arrow is kind of pre-described, has to be trying to make it perpendicular to the surface. Is that perpendicular? That looks pretty perpendicular to me. Do those look balanced?
Yeah.
Do they? I mean, if those are the two things acting, they don't look balanced to me. For every up and down, for every left to right, this looks a little bit down and to the right. In fact, I think if there's no friction, I don't think the calculator would stay there. I think there is friction. Something is preventing the calculator from sliding down the ramp. So whatever is preventing the calculator from sliding is friction. It has to be parallel to the surface. That means it has to be perpendicular to the normal force. These are those little things again. You get those in your notes so that you don't make this mistake. This thing I'm about to draw, it has to complement all the other things we've talked about. So friction is trying to prevent the calculator from going down the ramp. So I think friction must be up the ramp. And moreover, it needs to be parallel to the surface, so I'm trying to make sure it looks nice and parallel to that surface. But by definition, the normal force is perpendicular to the surface, and friction is parallel to the surface, so they must be at right angles to each other. And so now I've got normal force, friction, and weight. Now, if we want to do something with this, what coordinate system would you use? How would you draw the coordinate system? You have two priorities. Highest priority is to direct it in the direction of the acceleration. Is this accelerating? No. So the next priority is try and line it up with as many forces as possible. Yep?
Why is the friction arrow so much shorter than the other two?
Remember, it's supposed to show balance, right? You notice that this one points that way only about that amount. This one has to point this way about the same amount. And that's the only thing I was gauging it as. It's got to be the same in both directions. So what direction do you think we should draw the x direction? I mean, you really only have two choices here. You can line this up with the weight, or you can line this up with the other forces. Yeah.
You line it up with the x-axis, you have the friction.
So you're suggesting we line it up like this? I think that's a good choice. If I line it up like that, then that means the y direction has to be lined up with the normal force. I think that's a good choice. That's how I would probably do it. And make this the x direction and this the y direction. If I do it this way, then two of the forces are lined up with my coordinate system, but one of them isn't. Now, this is the biggest problem you guys tend to have with this stuff. If I tell you that the angle is here, where do I put the angle here? Don't guess. Guessing is hard. Which one of these will get smaller as the angle gets smaller? One or two? As the angle gets smaller, isn't the normal force going to go upwards more? As the angle gets smaller? So as I lower that incline, that normal force is going to point more and more straight up. Do you guys see that? That means that theta goes here. Now, if you don't want to try and figure it out, theta always goes between the weight and the axis aligned with the normal force. Just write it in your notes. If you don't want to have to figure it out, theta always goes between the weight and the axis aligned with the normal force. Now look, if you're going to break this up into components, net force equals 0, you would have to break this up into the net force in the x direction and the net force in the y direction. And I want to be really, really direct with you. Inclined planes are a big part of this class. They show up all the time because ramps and stairs, they show up a lot. And if you remember middle school, a wedge is a simple machine. It shows up a lot. So what we're about to do will happen the same way every time. It might be worth committing it to memory. We have to break the weight up into its components. And to do so, I'm going to draw arrows that represent the two components of the weight. I see this on tests every year done very, very badly. But it has to be a right triangle we're creating. So it has to look like this. They have to be lined up with y and x. I promise you, in this class, one of you is going to draw it like this. And I promise to hang that up on the board for us all to see. Okay? I'll take your name off of it, maybe. But that's wrong. Are those two things lined up with x and y? We're drawing a right triangle around the angle. The right angle always goes against one of the axes. Now, this side is the adjacent side, this side is the opposite side. So the adjacent side is going to be weight cosine theta, and the opposite side is going to be weight sine theta. I can't begin to describe how many times and ways we're going to see this. In fact, it's well worth noting that you could kind of memorize this. Not that. I don't want to say it'll be like this every single time, but it'll be like this a lot for inclined planes. That the part of the weight that's down the ramp is the part that goes with sine. And the part of the weight that goes into the ramp is the part that goes with cosine. Again, worth memorizing. In this problem, net force in the x direction equals 0, so we get weight sine theta minus friction equals 0. And we'll get normal force minus weight cosine theta equals 0. This is very common for inclined planes, and it shows up a lot.